Thank you very much. Thank you, Fabrice, for the organization. So, yes, my name is Alvise Benetazzo from the Italian National Research Council. My talk today will be a sort of continuation of what you have seen on Tuesday night in the wave remote pizza and remote sensing. And we'll talk how spatio-temporal observation can be used for the description of wind waves. So quickly, what space-time measurements are and how can be taken with focus on stereo wave imaging, of course, and then what measurements are useful for two cases, extreme waves and wave spectrum of different shapes. So let's start with a quick overview of dimensions of wave observation. So traditionally, waves are taken with a surface elevation eta function of time obviously. The given or variable spatial position x and y, and the typical output is a time series like you see and that you know very well. Then you can get eta function on x and y at the given time. LiDAR optical imagery give you this opportunity to have figure like that with the surface elevation is a 2D map. Of course, in this condition, you have to assume something connecting the spatial temporal scale, for instance, dispersion relationship. It is not necessary in the point you have a 3D spatial temporal data, where you have complete map of eta function of x, y, and t. As I will say, I will focus on stereo wave imaging, so a few words about the technique. So there are two cameras framing the same portion of the sea surface. They are synchronized, and via geometrical relationship, what you got is the 3D elevation here above the mean sea level. Here, the color is the elevation is overlying the images. So the typical size of the area you can frame is the order of 100 meter by 100 meter, and the spacing after gridding larger than 0.2 meters, so there is no particular limitation for the frame rate. It's more related to your hardware, but you can give it quickly up to 15 to 20 hertz. The good point, you directly have the sea surface elevation as an output, so you don't need any modulation transfer function of correction on everything. So it is a geometrical computation of the field. This is an example of the output with the same meaning of the colors I explained before. So you have one of the two images in the background, and then with the color map superimposed the sea surface elevation above the mean sea level in two cases, Yellow Sea and Adriatic Sea, where we have a permanent instrument installed. So the story of stereography for the measurement of sea surface height started 70 years ago, more or less, with the Chase et al. Project. It was a really smart way to figure it out, which is topography of sea surface. They used a couple on airplane and the ship in the common field of view to scale and keep control of things. Thinking that it was 70 years ago is a really remarkable example how things can be done properly. I suggest to read this report is available online. So let's go into the first topic. So how space-time measurement can be used to interpret extreme waves with the three subtopics: Rog waves, the so-called area effect, and the crest slowdown. So we have seen sometimes during the presentation during this week that we know that the highest waves travel with the wave groups most of the time. So we have the evolution of the wave group. This is area, different times, up to a point where they peak, and they focus. This is the case of dispersive focusing. They reach their maximum elevation. So you can easily see that the area where the maximum elevation is reached is pretty small. Just if you take a nice picture, if you set a threshold, for instance, 1.25 HS, this one used to define whether a wave is a RAG or not. Here we will have a RAG wave. In this position, we would not measure anything that be related to RAG waves, no matter what 1.25 HS has a limit, as a meaning or not. We will not to discuss that. Just to give you an example from space-time data. So we follow, this is a single time and the 2D map of eta over HS. We followed the large wave. At this point, well above that threshold, and then we took the time series disposition, and it looks like the blue line. A few meters apart here, doing the same technique, taking time series, because space-time is just a single map. You have the 3-dimension is time. There's nothing that exceeded that limit. So using time series, it's really difficult to judge whether C state had a rag wave or not, or if you can classify if it is a raggish or not. So we can use, at that point, space-time depth to catch rag waves. So using a movie like this, but of course not a movie's data set, and follow individual waves, and then where they exceed a certain limit, and then we got exactly, we freeze the time and take the time series that position over 30 minutes, just an example. We got 23 rag waves distributed in the area. This is a time series for all of them. In red, it is the average, which is a genuine rag wave shape for all the data collected during single sequence. Of course, this can tell a lot about can be the mechanism that generate freak waves. These are the observational points, the observational crest height put in EDF distribution, nothing related to the standard Rayleigh Typhoon Fedele distribution. For long crested C state is able to reproduce the probability of this type of waves taken in space-time, thanks to the work by Fedele in 2012, and then the late evolution, including second-order bound harmonics. It apparently seems that the generation and the explanation of the very crest height taken in space-time was dispersive and directional focus enhanced by second-order nonlinearities, which is a powerful mechanism to generate I waves, whether or not they exceed the drag wave threshold. Talking about extreme, we cannot miss the Draupner wave. So the Draupner wave, this record is very remarkable, probably the first example of very high wave. So 18-meter crest height over a significant wave field of 12 meters. So the crest to HS was 1.54. So it would be nice then, using a proper normalization of the Draupner time series. Here is red. It's here, so HS for the elevation and in period. And then from different data set, we collected which is the highest way we can got, data set, space-time data set in Station Papa, Aqua Alta platform, Adriatic Sea, Black Sea, and at Cazzivelli. So we then used the same scale. At the end, we found that the Draupner wave actually didn't have anything special. Was even smaller than other we found in our data set. Of course, it was a remarkable example, one the first get, but it seems that the world is populated with much more rag waves that we expect just using buoy data or whatever, because in any space-time data set of 100 meter by 100 meter over 30 minutes, we found tens or even 10 or even more rag waves. So this is a self-similarity shape, can be explained by the quasi-deterministic theory by Bocotti and some other, then extended to the higher order. So what is called the aerial effect is that, of course, since highest waves travel at the top of the group, if we increase the area, it could be possible that we found even larger and larger area. Crest elevation. So in 2013, Francesco Fedele examined it in this way, comparing which is the expected crest height over a point within an area and the crest height for the entire area. For it start from 1, but even for area 100 square meters, it jump to 1.3. So this is remarkable for the oil companies. They are really interested in that because they want to know which is the maximum crest height that can occur within the footprint of the deck. So that was later investigated by Malila using data collected, space-time data in the North Adriatic Sea, and found a good agreement between experimental data, still the maximum space-time crest height over the maximum crest height over time is fitted by nonlinear model that account only for second-order bound waves. And then playing more with some other data, integration of VAS, which is space-time data, with HOS, so numerical simulation, to prove the quality of HOS, and together with that, explore the areal effect for area much larger than the one defined by just the data. In this case, so the slowdown of the highest crest, it was an interesting phenomenon you can explore using space-time data. It is the way that the highest crest travel slower than expected. So this is an example. You can see this is a spatial transect for all max crest, breaking crest, and non-breaking crest. You can see that the leading wave just before the maximum, this is at the focusing point in leaning forward, and then after the maximum in leaning backward. And a representation over x and t give a distortion of the speed compared to what is expected by the linear theory by the local wave number. So if you compare what is actually measured with what is given by the relation, dispersion relation, you will find that the waves travel much slower than what expected, and when they break, probably because they are steeper, this reduction is larger and go to the number 0.8, around that number for very high crest elevation. Malila was not the first to get it. A few years before, Mike Banner et al. Using a numerical model of space-time and stereo data did the same, and this is the PDF of that ratio C over C0, 0.8 can be considered a good number for the reduction of the crest speed compared to what expected by the linear theory, and there's a cool explanation that takes into account the curvature of the envelope at the focusing point. You can find details and Mike and Banner et al. Publication and later publication by Francesco Fedele on that topic. So, second topic, we jump into the wave spectrum. So we have I already mentioned the early observation by Chase et al. That their goal was to find an analytical shape for the direction of wave spectrum, and actually they found something remarkable. Many years later, there was some other study, but my Banner to investigate which is the shape and saturation level of short gravity waves, use 3D data to get the two-dimensional spectrum kx, ky, then omnidirectional integrate over direction to get this funny shape k to the -3, which is then be used to parameterize the saturation level using U star and an empirical parameter. But the good point of having space-time data is that the 3D spectrum can be calculated all over the three-dimensional spectral space, so the energy, so the variance function of kx, ky, and omega, or frequency. This is the complete representation of the energy distribution and the dispersion manifold. Not easy to be interpreted this way because manipulating 3D data. Fabrice, the first day, already shown how to get a good view of that, just slicing the 3D manifold at the given frequency this way. So you have a 2D map. So 0.4 Hz is 55, 7, 85, 1, and 1.50. There are very interesting features in the spectrum. So let's start to have a look at the energy. So this is the energy of free waves that increasing the frequency of the slice, you will see they start departing from which is the peak direction of propagation, which is the bimodality that also Lionel shown during this week. This blob here is the bound mode. They are well aligned with the peak direction. They remain there, and and they're generated during the wave process. The different lines here are the dashed line is the dispersion relation without current, and the black one is with current, so the same for free modes and bound modes. So you can, from this, you can estimate which is the effective current and direction for each frequency, and Siemens knows how to invert from u function of k to the u function of z in order to get an approximation of what is the current profile over the vertical height. So back to the work by Sharp, I was already discussing these days. So getting the angular distance between the two lobes, it was easily found that waves away from the peak, so the small waves k over kp 40, okay. So 40 times kp, they are detached by 160 degrees. So so short waves travel orthogonal, basically, to the mean direction of propagation. Recently, Bernard Akawase and Lionel added an ingredient to this investigation, because Sharp just used the 3D surface to investigate the shape of the directional spectrum. But the good point you have with the stereo data, you don't only have the sea surface elevation, but you see waves. So you can play with the features of the images, in this case tracking the speed with the PIV of the crest. So in order to get an information of what is the crest line distribution for different phase speeds, so you combine the breaking statistic and wave directional spectrum. So this is 3D integration over omega, then you have kx, ky, and then Jacobian takes you to the k over theta. And the result is the one, it's already shown, but it is quite remarkable that you combine, which is the 3D surface elevation, to have this bimodal shape from the variance spectrum of the sea surface elevation and the distribution of the breaking statistic for different phase speed and direction. So the combination of the two explain why this bimodal is possible. It was a simple case with no current, so wind and waves where wind and current were aligned, but nevertheless, there is a powerful tool to investigate further things. I'm going to conclude with an example of stereo data collected from a ship in the marginal ice zone. Alberto Albarello was the leader, Miguel too was on board. The camera were used to both define the flow size distribution along into the marginal zone, together with the frequency spectrum, and how it attenuates within the marginal ice zone. So we have systems now that are able, just to conclude, measurement 2D plus time elevation field. I think we are reliable with the present technology for wavelength larger than 0.5 1 meter. We can combine with other instruments. Trig was shown how to can combine with echo sounder to get a 3D view of the bubble, or techniques for interaction study, air, sea, long and short waves, very nice, and breaking fade can be studied. There is a con, so collecting data is difficult. You need a platform. However, many data sets are readily available to be shared. Just I point you to one data set that Pedro Guimaraes et al. Organized. They are available, so 3D data in different conditions, the images too, if anyone is interested to use it. So please download, and if you have any question, come to us. Thank you for your attention.